Have you ever wondered how an AI really makes a plan? I'm not talking about a simple if this, then that kind of rule. I mean a complex, multi-step sequence to actually achieve a goal. Well, today, we're going to pull back the curtain on the clever technique it uses to map out the future one step at a time. It's called a planning graph. So, let's start with the big question. How does an AI cut through all the noise? I mean, think about it. For a robot or even a video game character, there are countless things it could do at any given moment. So how does it find that one perfect sequence, that golden path, that actually leads to success? That's the puzzle we're going to solve today. And we're going to break it all down into 5 parts. First up, we'll define the problem the AI is facing. Then, we'll see how it builds what I like to call a possibility map. We'll uncover its secret weapon for being so efficient, walk through a really simple cake example to see it in action, and finally, we'll weigh the pros and cons, where this technique really shines and, where it kind of struggles. All right, let's kick things off with a fundamental challenge. For any AI planner, the world is just a place of overwhelming, almost infinite choice. You see, for any goal you give it, an AI could try a million different things. And without some kind of structured approach, it would get completely stuck in what we call analysis paralysis, just endlessly thinking about all the options instead of actually doing anything. It needs a map. And that map is exactly what a planning graph is. It's the AI's roadmap showing it all the potential ways forward. So, a planning graph is built in these alternating layers. The first kind of layer is called a state level. Now, this isn't just what's happening right now. It's a big list of every single fact that could possibly be true at this point in time. Think of it like a snapshot of all the what-ifs. And the second type of layer, that's the action level. This contains every single action the AI could take, but, and this is the important part, only if its specific requirements are met by the facts in that state level that came right before it. So you start to see this awesome rhythm emerge, right? From a state of possibilities, we figure out all the possible actions, and those actions, in turn, create a new state of possibilities, which then allows for a whole new set of actions. The graph just keeps growing forward, literally mapping out the future layer by layer. Okay, but mapping out every single possibility, that sounds huge, right? Inefficient, even. Well, this is where the graph's secret weapon comes into play. It's a concept called mutual exclusion, or mutex for short. To put it simply, mutual exclusion is just the graph's way of identifying things that are totally logically impossible. It's like a rule book that flags pairs of actions or facts that just can't exist at the very same time. Here's a super simple example to show you what I mean. On the left side, can you have coffee and also have a mug? Absolutely, no problem there. Those two facts can coexist. But now look at the right. Can you simultaneously have your cake and also have it be eaten? No way, that's a flat-out contradiction. Those two states are mutually exclusive, and the graph is smart enough to see that and say, hold on, that doesn't make any sense. So how does the graph even spot these conflicts? Well, it's basically looking for 3 main things. First, inconsistent effects, which is when one action just directly cancels out another. Second, there's interference, where one action takes away a condition that another action needed. And third, you've got competing needs, where 2 actions require the exact opposite conditions just to get started. Okay, that's enough theory. Let's put all this together and actually see it in action with a classic AI planning example, the cake problem. We're going to follow these 5 steps, building the graph out layer by layer to see exactly how it solves this little puzzle. All right, step 1. We start at ground zero, state level 0, or S0. The facts of our world are really simple right now. We have cake, and it has not been eaten yet. Simple enough. Next, we build the first action level, A0. What can we do? Well, we can eat the cake because we have one. But can we bake a cake? Nope. The requirement for that is that we don't have a cake, and we do. So for this layer, only the eat action is on the table. Now for the next state, S1. This is where it gets cool. The eat action adds 2 new possibilities to our world, eaten cake and not have cake. But we also have to carry over the original have cake from the last state because, not eating the cake is also an option. So S1 now contains all of our potential future facts. And here is the magic moment. The graph scans this new state, S1, and applies its mutex logic. It sees have cake and eaten cake in there together and immediately flags them as mutex, a logical contradiction. This is huge.
It just pruned an entire impossible future from its search before it wasted a single second exploring it. Okay, now that we've seen how it works its magic, let's zoom out a bit for the final verdict and take a look at its biggest strengths and weaknesses. So the big advantages, well, planning graphs are fast, and they're fantastic at spotting impossible goals really early on. But, there are always trade-offs. They can be total memory hogs for really complex problems, and they have to assume that the AI knows everything about its environment, that it's operating in a perfectly predictable world. So, if you take one thing away from all this, it's this. Planning graphs work by first creating a huge roadmap of every single possibility, and then they use pure logic to cleverly erase all the impossible paths, finding a clear way forward. It's a really smart way to make a complex search incredibly efficient. And that really brings us to a final big thought. This whole method is powerful, but it completely relies on knowing everything in advance. It needs that perfect, predictable world, but what happens when you drop an AI into the real world? A world that's messy and unpredictable and just full of surprises? Well, that's a question for another time.